So, good morning again, and we continue with our second speaker. So, we do mathematics for the beauty of it, and once in a while this beauty is crystallized in moments of enlightenment, and one of these I vividly remember. That was the first time I read a paper by Greg, and I was working on a difficult problem with a friend and completely stuck, and we didn't know what to do. And then his paper appeared on an archive, and it just immediately became clear where we should go. And it's really like not often that happens, so it stays in your memory. And also one other thing this paper taught to me, that was a beginning of a series of papers with Odette Schramm and Wendell and Werner, is how important is cooperation in mathematics. So there were three persons, and well, when I met them and worked with them and talked to them, it became clear that all three of them brought different things to this project, and it's just combined efforts that resulted in several great discoveries. So Gregory Lawler went to University of Virginia and then got his PhD from Princeton with Edward Nelson. After working at Duke and Cornell, he, since 12 years, is a professor in Chicago. And his area of research is statistical physics, so it's a field between probability and mathematical physics. And it studies behavior of complicated systems composed of many small but simple parts. Because parts are simple, usually the problems are simple to formulate, but you get a big system with many simple parts, so they're usually very difficult to solve. And one of the things which really I admire in Greg is that he not only has ingenuity, but has persistence to solve these difficult problems, because we always face a choice, either try to write many easy papers or write one difficult one, so you should carefully choose a problem. And if you choose something really interesting, it's usually difficult. So not only you have to be smart, you also have to work hard, sometimes for many years. And then, well, when many other people gave hope, then you can prove something great. And I've read many papers by Greg, and I really admire both his ingenuity and persistence. And today he will speak about conformally invariant measures on loops and paths. And this is an area where these two qualities, they paid off, and indeed there are many interesting things already here, and I hope yet to come. So Greg, please.
Thank you very much. It's certainly a deep honor to have been selected to give a talk here. The area we're talking about is what's called critical phenomenon statistical physics. Roughly speaking, we're talking about various kinds of systems of random curves or fields with very strong interactions. Just roughly speaking, if there's often a parameter involved, which is temperature. We often look at inverse temperature, called beta 1 over temperature. And there gives basically three regimes. There's when the temperature is high, things are moving around a lot, and there's very short-range correlations. When the temperature is low, then there's very long-range correlations, and they go for a very long time. And the interesting thing in critical phenomenon is that the transition is very sharp. There's generally a critical value at which things change, this beta critical, and that's where I spend most of my time now looking at what happens at beta critical, because that's the one that's most closely related to unusual random walks and fractal phenomenon, which interest me. Now, for the systems I'm interested in, there's a lot of difference in the behavior based on the spatial dimension. A big thing for the mathematical world was in the theoretical physics literature in the 70s and 80s. Belevin, Polyakov, Zolotnikov predicted that critical systems in two dimensions exhibit conformal invariance. From a mathematical perspective, it wasn't exactly so precise what they were predicting, but it was telling us something to be looking for. By the way, I'd just like to say that we have this word predicted that a lot of us use sometimes for what happens in the physics community. I'll just say what's kind of behind it, at least in the people that I go for. When we say predicted, it means probably not mathematically rigorous, maybe far from being rigorizable, but yet we are acknowledging that there was significant theoretical insight going on. So it's acknowledging that there was a lot of work done, even if it wasn't mathematically rigorous. Now, in the 80s and 90s, there were many, many people. I've only listed a few names. I've listed a few names, the ones that are closest to the works that I was interested in, but they were using techniques of conformal field theory and Coulomb gas to make predictions about some of the systems I'll be talking about, and which you could actually tell, well, they were right because it matched simulations. Now, in the last 20 years, mathematicians have been able to make rigorous much of what's happening in 2 dimensions, and in fact, it's such a broad area in 2 dimensions now, so much has been done, that I'm only going to be able to sample some of this stuff, and I will say that I will sample a little bit the things of a little more interest to me, but that doesn't mean it's necessarily the most important. So discrete, we always go between discrete and continuous. Discrete models are often proposed, as actually our Stas said, because they're easiest to state, at least to state what the model is. But the idea is that for a discrete model is to understand what the model looks like when it goes very large, or as we often do, instead of taking the very large, we squeeze the very large down to very fine lattice spacings. And we often try to find a continuous model that's a scaling limit, and we go back and forth. Now, probabilists work both discrete and continuous. I'm really a probabilist. But in discrete, I've just listed combinatorics, experimentation theory, all these come into play. Continuous analysis, PDE. I should probably have geometry on both discrete and continuous. So there are actually many areas of mathematics that contribute into this. So we'll start with the absolute basics, which everyone should know, which is the basic of random walk. So here we'll talk about 2-dimensional random walk, and I just used complex notation, z plus iz, because we use complex variables. But basically, you're just walking around, and at each step, you randomly choose one of your nearest neighbors, plus or minus 1 or plus or minus I. Now, in the scaling limit, what you get is Brownian motion. So when I say a scaling limit here, this is probably very critical here. What we do is we scale space and time. So for today, most of the time, I'm going to scale space by n to the minus 1 over n. But then there's an amount that we have to scale time by, and that's the sort of basic dimension of the process. And I'm going to use a lot of red to indicate dimensions of things. So for Brownian motion, we have to scale time by the square of the spatial thing. This is sometimes called Brownian scaling or heat equation scaling. And basically, delta t looks like delta x squared. Okay, so some basic properties of Brownian motion. When we get to the limit, this 2, it becomes the fractal dimension of the paths. Or another way of thinking about it in terms of the Hölder continuity, that the change in space looks like change in time to the 1/2. But there are other things that the distribution is scale and rotationally invariant. And in 2 dimensions, there's a beautiful thing that if I take a holomorphic function, generally I'll do one-to-one conformal mappings, and I have a Brownian motion on one side, then the image of the Brownian motion is by the map F is just a Brownian motion. The only thing is we have to scale time for the fact that time and space scale. In this case, it scales, we have to change the time basically by squaring the factor in which we're doing it. And we do this locally by doing an integral. This goes back to Liouville. Okay, that's something we all understand now well. Let's go to something a little more difficult, self-avoiding walk. Well, this is very easy to state. I have a picture here. We have a little piece of a square domain, and we're considering all the self-avoiding paths, i.e. that's nearest neighbor paths that don't return to any point, and we connect them. And we want all paths of the same length to have the same probability. So what we're going to do is give each path measure e to the minus beta n, where beta is a parameter. Now what happens is if beta is small, one can take advantage of the fact that there's lots of paths, and the typical path takes up n squared steps. It's two-dimensional. If beta is very large, it costs so much to have a path that it wants to get from one side to the other as quickly as possible. It's effectively one-dimensional. And there's a sharp transition, beta critical, such that the walk switches from being one-dimensional to two-dimensional. And now, at criticality, we're going to emphasize this critical value, the typical length of the walk is conjectured to have about n to the alpha steps, where alpha is 4/3. In fact, this particular thing is still a big open problem in mathematics. This has not been proved. There's a picture of a self-avoiding walk. This is done by Tom Kennedy, who's one of the gurus in simulating self-avoiding walks. And this is the kind of path we'll be interested in today. Now, pictures like this of squiggly paths can be deceptive. We see this sort of squiggly path, but it's a lattice approximation. It's about 1 million steps or something. I'm not quite sure exactly how many. When we actually go to the continuum limit, we're going to get something which looks like a squiggly path, but it will actually be much more complex. In particular, for example, if I take any point, or at least almost every point on this curve, and I focus in on it, it actually winds infinitely often around every point. So this is actually a very complicated curve in the limit. Now, I also want to talk a little bit about scaling limits. The conjecture, if we take a scaling limit, is like we did for Brownian motion. The typical path, the path has k steps. What we do is we scale space by n to the -1, scale time by n to the 4/3, 4/3 being the scaling factor here. And the idea is this should converge to a probability measure on continuous curves. In this case, they should have fractal dimension 4/3. Now, this is very difficult. Okay, well, actually, the author conjecture, one way we can sort of guess from what the physicists told us is that if we actually get a limit, it'll be conformally invariant. That is, if I take it on one domain, take the limit, take it on another domain, limit, and I could get the same thing by taking a conformal transformation. But as I said, for the self-avoiding walk, this is actually still an open problem. Now, let me give you another model which is in between difficulty of simple random walk and self-avoiding walk. It's called the loop erase random walk. And it's derived from simple random walk. And what happens is you take a simple random walk. That is, when I say simple, I mean just normal random walk allows self-intersections. And the picture on the bottom left is a simple random walk from Z to W, restricted to stay in the square. And then I just deterministically erase the loops chronologically. And then that gives me a path that's self-avoiding, and it says it has no self-intersections. But the measure on the paths is a little bit different than what we had for the self-avoiding walk. It's still a measure on self-avoiding paths, but not quite the same thing. There's a path of a loop erase random walk made by Frederick Wicklund, and it's not the greatest picture. What the gray there is the simple random walk, or you can think of it as being the loops being erased, and then the red is a loop erase walk going through it. Notice loop erase walk only takes a small fraction of the steps of the simple walk. Now, the loop erase walk rises in other ways as well, and I just want to say a couple of them. One is a Laplacian random walk, and by that I mean you can take a path and you try to take your next step based on the solution of the Laplace equation at each step, or based on the probability a simple random walk would have tried to avoid the past. There's also a strong relationship between the loop erase random walk and uniform spanning trees that I will discuss very soon. And similar conjecture can be made about the scaling limit of loop erase random walk, but it turns out the fractal dimension is different. It's 5/4. But today I really want to emphasize a lot, not just the loop erase random walk, but also the field of erased loops that are there. That's actually, it's both the loop erase walk and the loops that have been erased that have turned out to be very interesting. Okay. So we'll get back to that in a second, but now I actually want to introduce a very simple idea. And it's simple enough we can actually give the definition. So a rooted loop is just a nearest neighbor in Z2, is just a nearest neighbor path that begins and ends at the same point. So, and we have the, what some people sometimes call the transition matrix for the simple random walk. It's just the matrix QXY, where QXY is equal to 1/4 if the 2 points are next to each other and 0 otherwise. And this thing called the rooted loop measure just gives each loop of 2K steps. I wrote 2K there because, if just for parity reasons, you can only have loops of even numbers of steps. And we just give each loop the measure that a simple random walk would give it, i.e. 1/4 for each step. So it's 1/4 to the 2K, but we add an extra factor and multiply by an extra factor 1/2K. It's just a very simple measure. And to some extent, this appears in various parts of mathematics, combinatorics. For instance, if it is in the total mass of this measure, it's actually given by a formula, a matrix formula that's known. So the total mass of this measure is, what I do is I take the determinant of identity minus Q. Here, I've restricted myself to a finite subset of Z2, so this actually is a finite matrix. Determinant of I minus Q. Take the logarithm of that, and take the minus sign. Okay, so this is a very simple thing, and the one simple addition to this that turns out to be very useful is, instead of thinking this about measure, what we do is we forget the root. So an unrooted loop is just a loop where I remember the order in which I do things, but I forget which was my starting point. So technically, it's a equivalence class of rooted loops, where two loops are the same if they're translations of each other. And the unrooted loop measure is just the measure of a loop is the sum over all the rooted representatives. So many times there will be exactly 2K representatives, but sometimes there'll be fewer. Now, since we haven't changed the total mass of this measure by doing this, the total mass of this measure is the same as we had before. I've just exponentiated it so we would get rid of that logarithm. And so I'm going to write f of a for the exponential of the total mass, which is just the determinant of I minus Q inverse. So this is just linear algebra. And this determinant I minus Q is called the Green's function. It could also be called, I minus Q is an example of a Laplacian. G also would be called the fundamental solution of the Laplacian in this discrete case. But for probabilists, we think of G of xy as being the expected number of visits to y starting at x until we leave A. Here we've given ourselves a finite thing. And now, given this loop measure, we actually have one of the constructions I want to talk about, which is a loop soup. It's a term that Fenton, Vernon, and I gave. And it's basically, you have this measure on all these possible loops, and they just keep coming, and you just keep putting them down. Mathematically, every particular loop comes at a certain rate using a Poisson distribution. So the number of times that a particular loop appears by time 1, say, or by time lambda and intensity lambda, is lambda times m of L. It's a very simple idea. Okay, now I'm going to talk a little bit about the uniform spanning tree. So if I have a finite piece of the lattice, I will look at a graph by taking the boundary and combining it into one boundary. Actually, I'm going to draw a picture here, which it's a little hard to see, but what I've done is there's a piece of the lattice, but I put the square in. That whole boundary is one set. So we have a graph, so I can talk about a uniform spanning tree on the graph. A uniform spanning tree, that's the short term for actually the uniform distribution on all spanning trees. That is, choosing a spanning tree from the distribution where every spanning tree gets the same probability. Now, there's something called Wilson's algorithm, which David Wilson developed a little over 20 years ago, which samples from the uniform distribution by repeatedly taking loop array walks. And the beauty of this algorithm shows the interplay of loop erase, random walk, loop measure, and soup, determinant of the Laplacian, all these objects. So I'm just going to say, there's a picture that's, you can think of this as being one lucky piece of the, we started by starting at a point on the inside, took a random walk till it reached the boundary, erased the loops, and put those in the tree. Once we do that, we now start at another point, take a random walk till it hits something that's already in the tree, erase loops, and keep going like that. I won't go through the details of this, but with this idea of this unrooted loop measure, it's actually not too hard to show that the probability that a particular tree is chosen in the algorithm David Wilson wrote is, well, it's 1/4 to the number of vertices times this f of a, this exponential of the determinant. The exponential of the measure, which is a determinant. Now, the amazing thing, if you've heard this algorithm for the first time, is that every single tree gets the same probability. So you actually say that every tree gets that probability. This is actually sampling from the uniform measure. And not just that, if you are sampling from the uniform measure and you know the probability of getting a particular point, you also know how many points are in your set. So you actually get that this is, the total number of spanning trees must be the inverse of this. And I've written that on that line there. So it's 4 to the number of vertices times determinant I minus q. And I wrote that last line. The Laplacian I'm using, I minus q, is not the same that combinatorialists tend to use. They tend to use degree minus adjacency. And in my case, that 4 to the number of vertices would just jump into the Laplacian. It would be that. So, and this is now an old result of Kirchhoff. And I should say that I'm doing this in 2 dimensions, but this is combinatorial applies to general graphs and networks, even with negative weights. But there's something beautiful about d equals 2, and that's it has a conformally invariant limit. So now I want to talk about the Brownian loop soup, and I'll think of it as being a limit of things. So I take a domain, think of the bottom as being a domain, and I put a very fine lattice there. And what I'm going to do is I'm going to put all these little random walks in there. I'll take the random walk loop soup inside that little lattice, scale things using Brownian scaling, get it smaller and smaller, and in the limit I get something called the Brownian loop measure. And the Poissonian realizations of it are called the Brownian loop soup. Now I've actually reversed history here in the fact that Wendland Vernon and I first defined the Brownian loop soup directly, and it was later that Jose Trujillo Ferreras and I gave the approximation of it by random walk measure. But one thing that's very useful here is that the random walks, the convergence to random walk to Brownian motion, there are very good estimates. But there's also this Brownian loop measure is actually a very beautiful object. Well, first, it satisfies a trivial property called the restriction property. It's trivial, but it's worth stating is that if I take a smaller domain, and I'm interested in the measure in the smaller domain, I get it by taking the soup in the larger domain and just restricting to those in the smaller domain. But more important to us is conformal invariance. So suppose I have a domain and I map it by a conformal transformation, one-to-one onto holomorphic map. So for each, if I have a realization of the loop soup in D, for each loop L, I can take its image under the loop soup. Now when I take its image, I have to be a little careful. I have to use Liouville's theorem, and I have to change the time parameterization appropriately. And the theorem is that that mapping from D to f of D, the image there is actually the same as the loop soup in f of D. But this is only true if we're looking this for unrooted loops. And this loop soup, continuous loop soup, really is a fundamental conformal invariance, something more people should be aware of. It's something that extends to much more into geometry, into surfaces and things like this. And very closely related to the determinant of the Laplacian on the domain. To determine the Laplacian, of course, you have to regularize somehow. In the same sense here, the Brownian loop measure is an infinite measure, and if you want to look at things, you have to take some kinds of regularizations if you want to compute something from it. Okay, that's for the loop measure. Now let's talk about the scaling limit of random curves. I'm going to now go back. Now we're thinking about the loop race random walk, and I want to talk about again the idea. We have a path, and it's in z-do. Suppose its diameter is of order n. If the diameter, that is the breadth of it's of order n, we can roughly talk about a fractal dimension, saying that if the number of steps is n to the alpha, that would be the fractal dimension. If I want to get a limiting curve, I scale space by 1 over n, and I scale space time by this n to the alpha. So now we have the rule change in space is change in time to the 1 over alpha. Or in some sense, the alpha dimensional length of the scaled path is n to the minus alpha. So the idea we'd like to do is to take the limit to get a measure on continuous curves on fractal dimension alpha. Now I'll just say, if we started with usual random walk and did alpha equals 2, the limit is Brownian motion, and this is a well-known fact, sometimes called Donsker's theorem or invariance principle. But before we go any farther, when it gets tricky this, I'd ask the question, what does it mean for a curve to be alpha dimensional? Suppose I have just a continuous curve from 0 to t alpha. There are 3 possible properties which are alpha dimensional-ish. The first is to look at the path, just the image set, gamma 0 t gamma as a set, and ask, what's its fractal dimension? When I talk about fractal dimension, I can talk about Hausdorff dimension, box dimension. I'm not going to worry about that for the moment. But look at that. Another way I can talk about is in terms of the Hölder exponent. So the gamma t plus s minus gamma t, the change in space is of order change in time to the power, 1 over alpha. Or I can also talk about how things conform by conformal transformation. So if I have a one-dimensional measure and I multiply the set by 2, it multiplies the length by 2. If it's a two-dimensional set and I blow the set up by 2, it multiplies the area by 4, 2 to the 2. And in general, for an alpha-dimensional set, you would expect the measure to blow up by an exponent of alpha. So you can say it is that the alpha-dimensional length, or the time to traverse the image, should be given by the scaling by the alpha. I've written that as the integral 0 to t f prime gamma s to alpha. Okay. Having said that, now we're going to back up a little bit and see what so we now should have this conjecture that there should be conformally invariant measures on curves. What do I mean by this? Well, today I'll think about as being probability measures on curves from connecting 2 boundary points in a domain. Right now I'll think of simple curves, and now here I'm using simple in a different way that I was using in the previous slide. I'm using simple in the topological sense of being no self-intersections. I might want the measure concentrate on curves of fractal dimension alpha. And I would like to say that if I take one domain, map it conformally to another, that the measure on one side goes to the measure on the other. And that's basically, if I'm D, look at the measure there. For each gamma, I look at the image of f of gamma. That gives me a measure on the other side. That should be the same as the measure on the other side. Just take a little careful here. When I go from gamma to f of gamma, then I've got to worry about the parameterization by this f prime to the alpha. There's another property which is called the domain Markov property, which a lot of these things, both limited self-voiding walk and loop race walk and other things satisfy. And I have it there by picture. By the way, this picture is by my student who just finished, Mohammed Jahangir Shahi. I actually was just at his defense, read his dissertation, and said his pictures were better than the ones I had in my slides, so I actually stole some of his pictures with his permission. So there's a domain Markov property. So suppose I'm doing a path from Z to W. So I have a measure of paths from Z to W, and I see a piece of it, say the red part. Then the distribution of the remainder of the part is exactly the same thing as if I was doing the measure from gamma t to W in the slit domain. So this is a good time to bring in, this is a picture of Oded Schramm, who unfortunately died in a tragic accident almost 10 years ago, but in many ways is the founder of the revolution in this area. And his idea was, if we consider simply connected domains D, we assume conformal invariance in a domain Markov property. And one last thing that he did was he considered curves modulo pre-parameterization. He didn't worry about this parameterization term. Then he showed there was a one-parameter family of such possible curves, which we now call the Schramm-Loewner evolution. And this is probably the main new building block of 21st century conformal invariance. So it's SLE kappa. I can't describe this very long, but I just want to give a very quick definition of it. So he does it in the upper half plane from 0 to infinity. So on the left-hand side, suppose you've seen the curve from 0 to gamma t, so I've slit the domain. If I slit the domain, because the upper half plane is simply connected and I've slit from the boundary, I still have a simply connected domain, so I can map it by the Riemann mapping theorem back to the upper half plane. That's what GT does here. And you do the right choice of GT, and you also do the right parameterization of the curve gamma, and then you find out that the map GT satisfies this equation. It's really a deterministic fact, going back to Loewner, that the time derivative GT of Z would be given by that equation, 2 over GT Z minus UT, where UT is the image of gamma T under that map. What Oded noticed was that, assuming all this was true, the only possibility for these conformally invariant domain Markov property things was for UT to be a one-dimensional Brownian motion, had to be mean 0, but there was one parameter, the variance of the Brownian motion kappa. One thing I really want to mention about this, interesting about this, and makes it tricky, is we're trying to define a curve, gamma, but we haven't actually said how the curve forms, except in the sense that it's a boundary of a conformal map. It's actually the boundary of the inverse map. So we just have, if you think of the inverse map as being from the upper half plane into some set, we've defined a curve as the boundary of a conformal map. And so suddenly the theory of the boundary behavior of conformal maps comes in. Now, despite this, we now know a lot of things about SLE. I've given a lot of names there for various people, but I just want to say a couple of the facts here. So for kappa less than 8, it's supported on curves of Hausdorff dimension 1 plus kappa over 8. So as kappa goes from 0 to 8, we go from dimension 1 to dimension 2 continuously, exactly one example for each kappa. When kappa is bigger than or equal to 8, it gets actually a funny phase where it actually becomes plane filling, the whole thing. I wanted simple curves, but actually the curves only stay simple up to kappa less than or equal to 4. Once kappa is bigger than 4, it comes in and touches itself, but bounces off. And there's also a reversibility in the sense that if I want to go from Z to W, it's the same thing as going from W to Z and then reversing the path. Actually, that's only true for kappa, actually less than or equal to 4. I have less than or equal to 8. It's less than or equal to 8. I have less than 8 there. It's also true at kappa equals 8. There's also another property of the curve, another way of thinking about it. And I can think of, suppose I have a curve in a domain D prime. That's the larger domain. And suppose I cut a piece of the curve away. And I ask, how does that change the measure of gamma? The way we talk about this in terms of radon-nicotine derivatives. The radon-nicotine is proportional, but when I want to talk about the radon-nicotine derivative in the larger domain versus the smaller domain, suddenly our Brownian loop measure comes in. So the radon-nicotine derivative in the smaller domain versus the larger domain is, it's e to this constant c over 2 times L, and L is the measure of all the Brownian loops in d prime that intersect both gamma and that perturbation, d prime minus d. And I'll note that that's actually a conformal invariant for conformal transformations of d prime. And this constant c, which is given in terms of kappa there, is actually something that comes from the conformal field theory literature. It's actually the central charge from conformal field theory. The two examples we've done here, self-avoiding walk, the measure doesn't care, the e to the minus number of steps doesn't care where you are. That's central charge 0. Perturbing the domain doesn't change things. If I do loop race walk, if I make my domain smaller, I have fewer paths that could actually produce gamma. That would actually mean that the central charge is negative. And in fact, in that case, it's negative 2. So one of the more recent topics I'm interested in, the SLE theory uses a capacity parameterization in order to get this Loewner differential equation to work. Basically, if you have this curve growing, the Loewner equation wants to make the curve smooth as viewed by someone far away from the curve, but doesn't necessarily look very good when you're really at the tip of the curve. And in fact, the parameterization is singular with respect to what I want to. I mean, we actually now know the exact Hölder continuity of SLE with respect to the capacity parameterization. It's on the left, but don't worry about that number. I'm not sure how interesting it is, except for the fact that it's less than 1 over alpha, which is what we would expect things to be. So a recent question is, suppose we see the curve. So we now have a curve, but we have it reparameterized the wrong way. In fact, we have it reparameterized in a way that's singular with respect to what we want. How can we find the right parameterization? Now, in an analog for a smooth curve, for smooth curves, sort of the intrinsic parameterization given a metric is the arc length parameterization. And what we want is the alpha-dimensional analog of that. So there's something called alpha-dimensional Hausdorff measure. And I won't go through the definition of that, especially because it's not very useful for us. Because random curves tend to have Hausdorff measure 0 at the critical value. It doesn't give us anything. But for random curves, a more naive concept actually works very well. Random curves are, if you have curves that are statistically self-similar, which you're trying to think of is, if you look at this curve and you blow it up, and then you blow it up much finer, and then you blow it up much finer, and you keep looking at it, what you sort of get are independent samples from your distribution. And when you have that, then the more naive concept of Minkowski content seems to work. And that is, you just take, it's a very simple idea. You have your dimension that you guess it to be alpha. Let's take it to be a compact set. You take what probabilists sometimes call the sausage, look at all points within distance epsilon, take the area of that. That will go to 0 if it's a smaller than two-dimensional set. So you compensate it by epsilon to the alpha minus 2, and you hope to take a limit. Now, for many sets in the world, this limit doesn't exist, but this does tend to exist for random sets, or at least we've been showing that it does. And it's related to occupation measures. So one of the states, so a few years ago, the former student Mohammad Rezai, we actually showed that the Minkowski content exists and is continuous and strictly increasing for SLE kappa paths. So in fact, we actually can parameterize the curve in the correct way. So we can parameterize the curve so that the Minkowski content at time t is t. And this is sort of the right parameterization. And this goes under the name natural parameterization, and it was sort of hinted at some previous papers of mine. Now, one thing we didn't solve at the time, but Dapong Jean has actually given a fairly short proof of, is the fact that we also get Hölder continuity with this. So SLE kappa with natural parameterization is, when I say weakly Hölder continuous, that's shorthand for Hölder continuous for all numbers strictly less than that, without saying exactly what happens at exactly that value. But think of it about gamma t plus s minus gamma t looks like s to the 1 stuff. So we now have the parameterized curves. Now, can we get discrete processes to converge to SLE? Well, there's a number of ways of doing this, and I'm going to sort of just quickly state there's a lot of processes. I'll just like to read that because I'm running a little short on time. But in all these cases, the discrete processes are shown to converge to SLE in the capacity parameterization. There hasn't been a way until recently, to talk about converging in this sort of natural parameterization. I should also say that for each one of these models, while there's this limiting object SLE, one needs to understand the particular discrete model fairly well in order to take the limit. I say that because at the bottom, it's still an open problem to prove convergence of self-avoiding walk. People sometimes ask me, we now understand why self-avoiding walk should be kappa equals 8/3 on a heuristic level very strongly, but we don't know how to prove it. People ask me why, and all I can tell them, the reason why we don't know how to prove it is because we don't know how to prove it. We know how to prove all the other things, but we don't have anything to give us for that. So I want to talk about some recent work for SLE2 for the loop race random walk. And that's to say that, in fact, loop race random walk converges to SLE2 in the natural parameterization. This is with Frederick Ficklin. And I want to say that this requires strong estimates both for the SLE and the loop race random walk. This does give a framework that works in principle for other discrete processes, but only if you can get the really sharp discrete estimates as well, which are much harder to get for other processes. Just a quick addition after I made these slides is there is work recently about Verholden, Lee, and Sun, building on work of Garbon, Pette, and Schramm for percolation exploration process in SLE6, but I won't discuss that except just to mention it right there. Now, I talked about the continuous. In order to get this result with Frederick Ficklin, we needed a fact about loop race random walk, which I kind of want to state. I don't really have a picture, but it's kind of an amazing fact. Take any subset, finite subset of Z2, and we're just going to make it simply connected. So simply connected means there's no holes in it, but it's finite. Take two boundary points and take a loop race random walk from one boundary point to the other. So what I do is go from one point to another, erase the loops, and now we take some point in the middle, we'll call it the origin, and ask, what's the chance that goes through the origin? And I'm making no assumptions whatsoever on the shape of this thing other than simply connected. And the answer is it goes to a conformally invariant limit. So if I've got this subset of the integers, I can think of it as being a domain by just replacing each of the little dots by squares. And the probability it goes through the origin is equal to up to an error. And it's, well, you take the conformal map. What's called RA there is the conformal radius at 0. It's the inverse of the map from the domain to 0. And I have two boundary points, Z and W, so I'm sending Z to 1, and W goes someplace. I'm just calling that e to the 2I theta. And then the chance of going through the origin is R to the -3/4 sine theta cubed, times some absolute constant whose value we don't know. But that constant doesn't depend on A at all, so it's an absolute statement. The errors are bounded uniformly, and they are exactly what's predicted by SLE2, but SLE is not used in the proof. Now, this result doesn't come out of nowhere. In fact, Rick Kenyon wrote a beautiful paper in 2000. By the way, Rick Kenyon is one of the speakers in this meeting, where he actually established the exponent 3/4 rigorously, and the 5/4 we gave is actually 2 - 3/4. But he his methods did not give a strongest result it was not strong enough to give the kind of results we wanted. I just want to very quickly go through the ingredients of the proof, partially to get to the names on the bottom. There's an ID of Kenyon, which is zippers, which is actually using the loop measure formulation with negative weights. It's very similar to looking at double covers, looking at square root maps. There are determinantal formulas for loop erase random walk that, they're somewhat from mean, but actually really can come from the loop measure formulation if you think about it right. You have to do potential theory for random walks with some negative weights. And you also have to use the sharp estimates of the random walk loop measure to the Brownian loop measure. The Brownian loop measure turns out to be the conformal invariant that really works in any domain. Now, this is particular to this thing, but I should say this in the spirit of discrete holomorphicity. And I mentioned 5 names there. There's actually more ... That's, I will tell you, we have our chair, who, of course, won a Fields Medal. Hugo Dumino-Copin, he'll be giving a talk. He'll be talking about percolation, which I won't be talking about. Dmitry Chelkov will be giving a talk, and he will be talking about the Ising model, which is where the discrete holomorphicity comes in. So I strongly recommend those talks for that. And it's sort of for the same reason, kind of the same reason this sort of stuff holds. Okay, so I'm trying to run a little short on time, so I may go a little bit quicker here. So let me just quickly talk about some other loop measures. So I was talking about the Brownian loop measure, which was Brownian loops. We can also talk about what you might think of as being SLE loops. Loops that I did SLE going from boundary point to boundary point, but we can also do loops that go from there. So let's look at we can look at formal loop ensembles can be collections of non-intersecting loops that locally look like SLE kappa paths. Here I'm doing kappa less than or equal to 4 for the simple path case. For SLE 8/3, this was done in sort of general domains by Vedel and Werner. Actually, in simply connected domains, it actually can be done by work of Oded, Vedel, and myself, and was really predicted in work of Mandelbrot in his book, where he drew pictures where there's a relationship between the frontier of a Brownian motion and an SLE 8/3 paths. Now, for kappa between 8/3 and 4, there's a couple of ways of constructing it. I'll just talk one of them, and that is by taking my Brownian loop soup. We look at the Brownian loop soup with a particular intensity. You take the right intensity for that Brownian motion, having to do with the central charge, and almost every point in the plane is covered by loops, but there are exceptional points that are not. And these give you paths, and so basically the weight of a path is given by sort of the probability that no loop will hit a path, at least that is on the discretely. And these arise in a number of places. One place where it comes up is the Ising model, and I've just given one paper there where the scaling limit of the boundary of the clusters is CLE3. That's red, white, on glide. But they come up in a number of ways. But this is 8/3 to 4. This is this is positive central charge. I just like this phrase, loop erase loops. Almost loops and spanning trees. For a negative central charge example is if I take a spanning tree, well, a spanning tree won't have any loops, but you can talk about an almost loop in a spanning tree, a big macroscopic thing that's there except for one edge. And you can actually write down what the probability of this appearing is, and I won't look at this formula very much. There's 3 terms to it. One is just 4 times the length of the path. Then there's this FL of A. That's the exponential of the measure of loops in A that intersect L. Those are the loops that have been removed to get there. And then there's one last term, which is a conformal invariant, but I don't have really time to describe it. But what happens is, basically, there's a local piece. The local piece is the 4 to the number of steps and the contribution of FL of A by small loops. And then there's a large-scale thing, which is the contribution of FLA by large loops, and this R is actually a large-scale thing. And there's one last thing we talk about, which I was interested for a long time in constructing these using SLE loops. But this is, we take an SLE, and we want to define things like the Brownian loop measure. We do a SLE loop from one place to another. But in order to do this, when I find the random walk loop soup, I need to divide by the length of the curve. We need to do this for the SLE loop soup. And this can be done, now that we have natural parameterization Minkowski content, you do something and then you tilt it by 1 over the length of the curve. Unfortunately, I and Lori Field, the student I was working on this, weren't able to complete this, but Dapeng Zhan has very recently completed an important final step for this. But I'll just say you still need to understand boundary effects. But now I want to jump a little bit, and running short on time today, so I want to get some of this discrete versus continuous. Okay, this is a picture of my advisor, Edward Nelson. And I want to give him a little, there's a certain philosophy that I got from him that I like, which is that you don't really know what's happening on the small level. You see the world, what he would call the standard part of the world, but what's happening very microscopically or infinitesimally is hard. So I will think about, look at some stuff in infinitesimal lattice. But you could just think of n being very large. I'm going to define some stuff there. Let's think of having a domain in D, and we're going to have a very fine little lattice. So the discrete Gaussian field, which came up in one of the talks yesterday, but one way of thinking about this is what we're going to do is we have this domain, we have all these points. We'll start with white noise. White noise, we just put an independent normal random variable, 0, 1 random variable at each point, completely independently. I'll call that white noise. What we're going to do is put some order to this by weighting by the having points next to each other like each other. So we're going to tilt by e to the beta times this term. This turns out to be very easy because I go from a Gaussian distribution to a Gaussian distribution. And what happens is I tilt by the joint distribution just becomes what's called a joint Gaussian distribution with a certain covariance matrix. And the covariance matrix is actually just the Green's function. It's the Green's function for the random walk. If beta is less than a quarter, the random walks die quickly. The random walks die. The critical value is beta equals a quarter, where we only have death of these random walks when they leave the bounded domain. So here's a picture of the Gaussian free field. It looks like this. This is a discrete version of this. So there's a continuous Gaussian field, and it's obtained from the discrete Gaussian field by taking a limit. There's a little tricky thing in the limit because the variance at a point blows up. So you actually, in the limit, you actually don't have something well-defined point to point, but it's only a logarithmic blow-up, one of the mildest things you can talk about. So it's actually fairly easy to define this in terms of a distribution generalized function, and and we can define it, and we actually get a conformally invariant object. Now, there has been work relating this to the loop soup. I like the loop soups, and I wanted to go to very quickly work of Lejeune and Lupu and others, that you can actually, instead of getting the Gaussian free field, you can take the loop soup. So we'll take a realization of the random walk loop soup at intensity 1/2 rather than 1. This gives me an occupation measure. For each point, we have how many times it has been visited by a loop. Then this could be a discrete field. I'm going to call it 2nx plus 1. And I'm going to say that's approximately the distribution of the square of the Gaussian field. That's not exactly correct because I have integer valued random variables there. But the actual exact thing is gotten by replacing the 2nx plus 1 by 2n plus 1 independent random variables with a certain distribution. So you actually get this thing, so you actually can get the square of the Gaussian field using loops, The way Lejeune and Lupu do it, they actually use a continuous time version of the loop soup, but this adding this random variables has the same thing. And this is also very general. You can get Gaussian fields with different covariances by putting different weights on the loops. You can get negative covariances or complex fields with correlated real and imaginary parts by using signed weights. This is more speculative than knowing, but you also consider weights for more complicated, non-commutative situations. I should say this is not, I mean, a lot of math one does is not new. There's certainly things from this in Szymanczyk, in Bridges, Freilich, Spencer, certainly in Dinkin and many others that have related fields to integrals over paths over loops. But this explicit formulation is sort of new. In terms of SLE, I'll just to give you a sort of name dropping a little bit here, there is a way of looking at SLE by starting with the Gaussian field and using the Gaussian field to tell you tell you how the SLE should move. I won't go into this except this goes under the term imaginary geometry, and Scott Sheffield and Jason Miller are probably better. There's a important paper of Dubé-Da which started some of this, but I won't have time for that. I do want to talk a little bit about another idea of Liouville quantum gravity, and just to think of this a little bit, if I have a conformal transformation, we had this f prime to the alpha term, which told me how to change the length of something. Well, instead of going somewhere else and looking at the length somewhere else, I can stay where I am, but I can use the length from the other place. In other words, I can change the metric. So the idea of, so we can think of changing this f prime term as being e to the phi of z over 2. That's just terminology. And we think of it as being a change of metric on D. So we're not changing the topology of the disk, but we're changing the metric of the disk. So like, for instance, we would measure the length of an SLE path by the kind of formula we had there before. Now, this idea is actually to choose phi to be random. It's actually, we're going to choose phi to be the Gaussian free field. So for this Gaussian free field, so what do is we take the Gaussian free field. I put a square root pi over 2 there just to scale it the right way. So we have a Gaussian field. So at a point x, the expected value of the field squared is log n. What I want to do is take e to the lambda phi. Now that's a good time just sort of stop and say, in this slide is a short version of what people in statistical mechanics and large deviations and things like that do all the time. We're interested in behavior e to the lambda phi. The first thing we do is compute its expectation. That's the partition function. For a Gaussian integral, that's actually very easy. And the second thing we do is, after we normalize by the partition function, what does the typical thing look like? So in this case, if I take the expectation of e to the lambda phi, it looks like n to the lambda squared over 2, so I'll divide by that. And while I'm doing that, I actually check that if I look at this thing, it's concentrated on points where y looks like n to the lambda squared over 2, and the probability of those points is n to the minus lambda squared over 2. We're actually seeing what the behavior is. And therefore, we see that the standard part of the measure is supported on a set of fractal dimension 2 minus lambda squared over 2. And lambda squared equals 8/3 is closely related to random planar maps, triangulations, quadrilations, Brownian map. I would like to tell you to go to the talk of Jason Miller. I cannot because it was yesterday, but Jason Miller gave a very nice talk on the ideas in this and the work on that. Lambda squared equals 4 has to do with the maximum of Gaussian field. I should say, I'm using lambda here. Gamma is the standard notation, but I'm using gamma for something else. Okay, so there's something about the KPC, but I'm going to skip that because I'm running short of time and I want to talk a little bit about higher dimensions. So Self-avoiding walk and loop race in higher dimensions are interesting questions. For both loop race and random walk and self-avoiding walk, what's called the upper critical dimension is 4. And that's a simple geometric reason. Back to the Brownian motion. The Brownian motion is a two-dimensional set. Suppose I want to put a self-avoidance constraint on a two-dimensional set. That says the past and the future of a set cannot intersect. Well, how strong a restraint is that? Well, it has to do with, do you expect two two-dimensional sets to intersect each other? And the critical dimension for two two-dimensional sets to intersect each other is 4. So for d greater than 4, both the mean squared distance of loop race walk and the self-avoiding walk is the same as for usual random walk, and the scaled paths go to Brownian motion. I proved it for loop race random walk. For self-avoiding walk, there's a series of papers, Bridges, Spencer, Slade, Hara. I should say that the self-avoiding walk problem is significantly harder than the loop race problem here, so they should get more credit. In 4 dimensions, you actually expect convergence to Brownian motion, but with logarithmic corrections to the scaling. So for loop race random walk, the mean squared distance looks like n, but the correction is log n to the 1/3. That was proved by me. For self-avoiding walk, the mean squared distance looks like n to the log n to the 1/4 and scaled down. Now, I really can't announce this result because as far as I know, it hasn't been completely proved, but there has been considerable progress by David Bridges, Gordon Slade, Bauer-Schmidt, and they have very close partial results for similar but not exactly this model. So it's getting there. That leaves 3 dimensions. And this is the topic for ICMs in the future. We actually live in a 3-dimensional world. Tools of conformal invariance are not available. An interesting thing, critical exponents are expected to exist, but it seems like they actually take on random-looking values. For instance, Flory originally, who did the self-avoiding walk, predicted a length of n to the 3/5 for a typical self-avoiding walk. By the way, what's written there is nu is 1 over the dimension. But now it doesn't seem to be right, and you get about 0.5888 ... For loop race random walk, it grows a little faster, which means it's a little thinner. But again, numerically, we have 0.61 ... Rigorously, we know it's bigger than 0.6, but almost surely strictly bigger than 0.6. The loop race walk is kind of a natural candidate to understand some progress by Schramm, but we'll leave the question, so maybe I'm just out of time now. I will leave the question, can we construct 3-dimensional continuous processes that are the candidate for the limit of loop race walk or self-avoiding walk? The Schramm-Loewner evolution is an indirect construction, so it's not so good. Can we actually find good ways to construct continuous models to do this? And can the Laplacian motion perspective help here? And I'm now told I'm out of time, so this is a good time to probably stop, and I thank you.
So thank you very much. And I was told that you are not allowed to ask questions, but I am allowed. What is a talk without a question? So what should we do next, dimension 3 or dimension 4? And if dimension 3, what would be the first thing one should try to prove?
Well, there are people, since it's work that's from the early stages, who are trying to take the scaling limit of loop race random walk, show its existence, and on the other side, trying to construct a continuous process that would be the natural candidate. And hopefully those two would then meet. But attacking from both sides seems to be a useful thing to do here. 4 dimensions for the loop race random walk, I think we now understand. And for the self-avoiding walk, send an email to Bridges, Slade, and Bauer-Schmidt, and they'll tell you, I don't know exactly the stat, but what they've done is taken a lot of work to get where they've gotten there in 4 dimensions. And what I have left out is 3-dimensional self-avoiding walk And I have no idea there at all.
Okay. Well, thank you and good luck. And thanks again to Greg Lawler.